All right, so today we are actually going to start our unit on organic molecules, chemistry and biology. And one of the very first things we want to be able to do as a biologist is identify whether a molecule is organic or inorganic. And our definition of organic means that it has to have both carbon and hydrogen in the molecule. And that's how we're going to define that. So as we build things today, because we're going to make a couple of three-dimensional models, you want to practice that skill. Just double check, does it have carbon in it? Does it have hydrogen in it? If it has both, it is considered to be an organic molecule. So we're going to look at just three types of atoms today. We're going to be using yellow spheres like this one right here to represent hydrogen. Notice it only has one hole in it. That's because hydrogen atoms can only hook to one other thing. They can only make one bond. You'll learn a lot more about bonding in chemistry. I just want to point that out right now because it's going to be important as we build these molecules that we fill all of those spaces with other atoms. If I were to try to build a model and I had a space that wasn't full, that means I'm not really following the rules of chemistry properly, and it's not a molecule that would probably actually exist in nature. So we just want to make sure that all those spaces are filled up. We're also going to be looking at oxygen. We're using red to represent oxygen. Oxygen is going to make two bonds, so it's got two spots on it there that we can fill. And then we're going to be using that all-important carbon. And we're going to use a black sphere to represent carbon. And it actually has four, a little hard to see probably, openings in it. So carbon will make four bonds. Since carbon can make four bonds, it can bond to a lot of different things. And it will actually tend to be the central atom in all the molecules that we're going to be building whenever we use carbon. So if you have carbon in a formula that you're looking at, a chemical formula, or you know that it's present, if you are trying to figure out what that molecule is going to look like, what its shape might be, you want to consider just putting carbon in the middle to begin with. All of the carbons may be hooked together in a ring or a chain, and then building off of that, because that's the way that most molecules are going to be made. So we're going to start with something that you're very familiar with. We're going to start with some H2O, water. And I always like to tell my students that water looks like Mickey Mouse. So I need H2, two hydrogens. And I need one oxygen. So I've got two yellows and a red. Kind of rolling away on me. I need a better surface to work on. I'm just going to use a couple of wooden dowels, some sticks, to connect these guys together. So I've got hydrogen connected to an oxygen. That oxygen has one more spot open. Boom, boom. And there's Mickey with his two giant ears. I have an oxygen in the middle and two hydrogens coming off of it. There's my water. Next, I'm going to build an oxygen molecule, which is O2. You might remember that from some of our equations we looked at before, respiration, photosynthesis. When oxygen is found in nature, it's not just one oxygen atom by itself. It actually has a partner. Fancy word for that is a diatomic molecule, if you're getting really cool. But again, that's kind of more chemistry than biology. Because this has two bonds between it, we have to hook these same two atoms together twice. That is called a double bond in chemistry. So I have two oxygens, each of which has two spaces to connect. So I'm going to make two bridges in between these two atoms. This is a molecule of O2. You might want to ask yourself right now, even though oxygen is really important to living organisms and water is as well, are these molecules considered organic or inorganic? Something to consider, kind of the goal of today. The next thing I'm going to make is carbon dioxide, another molecule we've talked a lot about when we looked at our respiration and photosynthesis in Unit 1. I'm going to start again with that carbon atom, and I'm going to hook everything to it because that's my central atom. It has the most available spaces to fill. So I'm going to put a carbon on either side of this guy. Sorry if that's too close to the camera for you. But I'm not done yet because I still have spaces available on this atom to fill. So I'm going to make a couple more double bonds, kind of like we saw a second ago in our oxygen molecule. I'm going to hook from the carbon to the oxygen again. And I'm going to hook from the carbon to the oxygen again. Whoa, try not to break it, Mrs. Reiser, come on. And what I wind up with is, oops, sorry, that's very squeaky, one carbon atom with two oxygen atoms hooked to it in a nice, actually kind of straight line. That is CO2. So not actually that different looking from oxygen, but behaves really differently inside of living organisms. Last one we're going to do is methane, CH4. So 1 carbon, so I'm counting my atoms, which is always good to do when I'm looking at chemistry. And then 1, 2, 3, 4 hydrogens, if you can see that. Adjust the camera a little bit. And again, I'm going to start with my carbon in the middle. And because there's 4 atoms of hydrogen here, CH4, I'm just going to stick 1 hydrogen to each of those spots on my central carbon. I'm going to make what we call 4 bonds. And I will get a nice methane model. For those of you that like geometry, looks kind of like a tetrahedron, which actually is the shape that it would have in chemistry. So there's my methane. Your follow-up question here that I really want you to think about is, of all 4 of these models, water, oxygen, carbon dioxide, and methane, which are organic?